anything horrible that we've done so we've missed. Okay. All right, for anybody watching the video, I just went over Appendix A and Appendix F, and come see me if you've got questions. All right. So in our book on section 1.4, if you would look at the bottom of page 35, bottom of page 35. Now, I normally am opposed to people standing up in front of the room and reading to everybody, but some things are important enough to do that, and I'm going to do that right now. So as you're looking here on the bottom of page 35, it says the derivative is one of the two most important concepts in calculus. The other one is the integral, right? We've already talked kind of about those, the derivative and the integral. We'll devote much time and effort to derivatives. The basic idea behind derivatives is simple. For a given function f, the derivative function denoted by f prime, that little symbol means f prime, tells the rate of change of f. So here's the story. So we have a function f of x. We're going to call this, to start here, just some amount function, if you will. Okay? So we've got some function called f of x, and you'll see what I mean by amount function here as we go through the next few days. But this is some function, and its outputs are an amount of something, okay? Let's say in our example it's going to be a position function. So that means the position of, we're going to talk about a car here in a little bit. So let's say we're talking about a position function. That is, miles would be our units, okay, as this car travels along. So this position function would be the amount of miles that this car has traveled. All right? Associated with that function is going to be this function we're going to call f prime of x. That little symbol up there is read f prime. And we're going to call that, among other things, the rate function. Now the key though is it's associated with the f function. That's why we don't call it g. We don't just call one of them f and one of them g. We want to understand that this function is associated with the f function. So therefore we use the name f prime. Now, remember when we did that door swinging problem, right? And we talked about degrees per second, how fast it was opening. And we used the term rate of change. And we used the term average rate of change versus instantaneous rate of change. We're talking about instantaneous rate of change here. Okay? So this would be the velocity function for this particular situation. The rate of change of miles in our example here is going to be miles per hour. Just like on that door swinging open, it was degrees per second. Degrees per second. Here it's going to be miles per hour. It's the rate that our position is changing. All right? This is called a derivative. That is the term that we have. This is called a derivative. A derivative function is a rate of change. Okay? Now, we're not going to get into this for a couple of days. We'll probably get into it a little bit on Friday. So I would say don't write this down right now. But we could even go off of that function and do the rate of change of it. What would be the rate of change of miles per hour? That's acceleration. You've been in physics, you've talked about that. If you change your velocity, that is acceleration. That would be, acceleration is miles per hour, or a lot of times we'd say miles per hour squared, but it's miles per hour. It's the rate of change of velocity. The name we give that is f double prime. The derivative of f prime, we need another prime. And we could have a triple derivative and a quadruple derivative, but we won't. Hardly ever, right? There is, actually in physics, there is a name for the rate of change of acceleration. It's called a jerk. After that quiz, it's fitting. Some of you probably called me that. after you saw your grade. But anyway, right? Different kind of jerk. Acceleration. If you think of a sudden change in acceleration, right? You can see why maybe they would call it jerk, right? But that's, ask Mr. Orwell or Mr. Mandernet. They might know. Ask them if they've heard of jerk. Be careful how you say it. All right. Did you talk about it?
No.
Oh, you never did. Okay.
I might know about it, but I don't.
You don't. Come on. All right. So Etway's only been teaching years. So anyway, higher order derivative is what we call it. So if we want to get into a second derivative, a third derivative, those kind of things, it's just the derivative of the derivative. So any function can represent an amount function. So in this case, what I'm just talking about here, f is your amount, this is the rate of change of that amount. But if we talk about acceleration, this becomes the amount function, right? It's the amount of velocity you had, and it's the rate of change of that amount. So when we talk about an amount function versus a rate function, any function you have, the rate of change of that function is called the derivative. All right, now we can think of it in a graphical sense pretty easily. Let me erase this. So now if you want to write this down, graphically, it's always the y units divided by the x units. So if I have this function f of x, and it's miles here, and it's hours down here, then the f prime function is always going to be the y units on f divided by the x units on f, and the x units are always going to stay the same. Because it's f of x, it's f prime of x. They both have x as the input, but their output units are going to be different. It's always going to be that way. And now you can see why acceleration is miles per hour. Because if you do another derivative here, you take these y units, miles per hour, divided by those y units, so you get miles per hour. Okay? It's the rate of change. All right, so the derivative graph is always going to be these y units divided by those for its y units. All right. Now, they give you a picture at the top. Turn to page 36 then, if you haven't already. In the blue box, it gives you this informal definition. It says the derivative, we're going to define it two ways. The first way we're going to define it is as the instantaneous rate of change of f. So that's what a derivative is, the instantaneous rate of change of f. All right? So if I wanted to write that down, so if we want to talk about f prime of x, okay, one, it's the instantaneous rate of change of f, and this could be miles per hour, this could be dollars per pound, this could be feet per second. I mean, any sort of a rate, right? Any sort of a rate. When I sell 1,000 pounds of product, how fast is my profit increasing? Right? That might be something we'd be interested in finding. The rate of change. Right? That would be dollars per pound. Okay, but velocity is one we use a lot. Position velocity, which we're going to talk a lot about today. Now there's a second way we can define f prime of x, which we'll come back to here in a little bit. All right, so this picture right here, all right, is the top of page 37. So I want everybody to look at that picture right now. And try to use some colors here. Start with red. All right. This is, and if you read at the bottom of page 36, it says, here we have a situation. We have a car is going to leave Bismarck, North Dakota. I think that the textbook authors were originally from around that area. They used Bismarck a few times in this book. Bismarck, North Dakota. We're going to have a function here called P of t. P of t is going to be the position east of Bismarck in miles. You can see right there it says miles. This is going to be the velocity of the car, the eastward velocity of the car. Okay? Now, it's important we understand the term position and velocity. This is different than distance and speed. Can somebody tell me the difference? Distance and speed, how are those two quantities different than position and velocity? direction. Distance and speed do not have direction. Distance and speed are always positive values. Speed is just how fast you're going. Distance is how far you've traveled. Position says where you are also. And velocity says what direction you're going. So in physics, you've been in there, you've probably talked about this a bit. So this is Bismarck right here at 0. Think of an x-axis here. East, west. If I'm going this direction, my velocity is positive. If I'm this side of the Bismarck, my position is positive. If I'm over here, if I'm going left, my velocity is negative. If I'm left of Bismarck, west of Bismarck, then my position is negative. Now, is it possible for your position to be positive and your velocity to be negative? Yes. If your position's positive, what's that mean? I'm over here. If my velocity is negative, I'm moving this way. So I'm over to the right of Bismarck, but I'm moving left. That would be position positive, velocity negative. Okay, so here's what I want you to be able to do. Next quiz. This will probably be one of the questions. I'll give you a situation like this where I describe what these positions mean. Oh, and by the way, what's another name for V of t? We just learned it. P prime of t. There you go. V of t, another way of writing that is P prime. Matter of fact, that's the way we'll mostly write it. We will hardly ever write it V of t. We might still, it'll still show up. But that is the derivative of position. That is P prime. All right, so one of the questions I may ask you on our next quiz might be this. Given this situation, pretend you can't see these graphs at all right now. Okay? Well, what the heck? We don't have to pretend. Just go to this. Of course, you still got your books, I guess. P of 3 is 165. So I give you the situation, and I write that, and I say, tell me in words what this means in this situation. Who wants to try? Go ahead.
Is it 3 hours or 165 miles east of Bismarck?
Almost perfect. And the only qualm, and it's really good, it would be full credit. But we do know a little more about the situation. I didn't read it to you, that's why I would say it's still okay. What does it say about the time? Time 0 is what? When do we leave Bismarck? Noon. So at 3 p.m. would be just a little better. But I love how he said at 3 hours, because that's the instantaneous part of it right there. At not our average or whatever. This is not how far we traveled. He didn't say that, right? He didn't say we've traveled 165 miles an hour, because does this say how far we traveled? It does not say that. Why could the distance we traveled be different than 165? We could have went back and forth, and we forgot something, and then we went this way and that, whatever. All this says is that at 3 p.m., we are 165 miles east of Bismarck. Could we be stopped? Could we be going east? Could we be going west? Absolutely. Now again, pretend you're not looking at those graphs. All we know from this information is at 3 p.m. we're 165 miles east. Now, if we combine that with that means we're not moving. P prime is the rate of change. If our rate of change is 0, that means we're stopped. So we're 165 miles east, and we're stopped. And I think if you go back to those graphs, that is exactly what this shows. Right here, P of 3 is 165, and right here, P prime of 3 is 0. And so I want you to notice the connections between these two graphs. Now, we're going to spend the next 7 days talking about the connections between these graphs, probably 6 days, and then we're going to have a quiz. Our next quiz will be next Thursday. So we're going to be doing this for a while. So the fact that you won't be experts at it by tomorrow shouldn't bother you, okay? But notice that when this is at this peak, we have this. Now what else? I have another peak down here. This is a change in direction, isn't it? So he takes off and he's going east of Bismarck. Then he turns around and comes back to Bismarck. So he's going west. Now where's he doing? He's still going west, but now he's west of Bismarck, but then he decides to turn around and come back to Bismarck. Well, when he turns around at 6 point whatever there, that would be this point right here. You notice the peaks and valleys of this graph are zeros on this graph, right? Important to understand. Also, what direction is he going during this time period right here? He is going east during this time period. From here up to here. Also going east during this time period. Right? What does that correspond to over here? All of these values are above the x-axis. They are positive. So the y values over here seem to correspond to the direction we were going here. Here, this is west, and that's when all of these values are negative. So the up and the down of the left graph corresponds to the above the x-axis and the below the x-axis on this graph. Does that make sense? Up here is above, and down is below. Yes? Here? So right here when he's coming towards Bismarck, right? Why are they negative? Good question. Because he's over here, east of Bismarck, but he's coming back towards. So anytime since the velocity was defined to be eastward velocity, anytime he's going west, he's going backwards, that's negative. That's why. Okay, so you're exactly right. Even when we cross here, it still is negative. Why? Because we're going down. We're going westward the whole time. It's just that he was over here east of Bismarck, goes west, 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 gets to Bismarck, and keeps going west. Right? So his velocity is negative that whole time. All right, now, back to our notes. The other definition of f prime is the slope or slopes of f of x. Now, and we should understand this from Algebra 1. Rate of change is slope. Now, one little difference. When I say the slopes of f of x, I believe, oh no, that's all it says. What do we mean by the slopes? Well, I've got another picture here, and we'll come back to this picture here in a minute. When we talk about the slopes of a curve, and this is farther on page like 39 or 40 or one of those pages, but when we talk about the slopes of a curve, what we talk about is the slope of the tangent line. And I think I mentioned this when we were doing that degree problem. I talked about a tangent line. Now in algebra class, you need 2 points on a line to do slope. The problem with tangent lines is we only know 1 point. We know the 1 point on the curve. We don't know the other points. So we'll have to talk about how we get those points. Matter of fact, in one of the ways, though, is we get it off of our graph. Like on that graph, on that picture we had over here. How can I get the slope? How can I know this slope right here? I'll look at this graph and look at the y values. Does everybody see that? These y values are not only the direction that the car was going, but it's the slope of this graph. Notice the blue graph, when it's going up, has what kind of slopes? Positive slopes. So these, and I can't say this often enough today, the graph of P prime or F prime, the y values on P prime are the slopes of P. The y values of P prime are the slopes of this graph. So another way to think of the derivative graph is a plotting of the original graph's slopes. So down here, what we just wrote in our notes, okay, f prime is the slopes of f. What we mean is when we plot the f prime graph, we are plotting the slopes of the f graph. Now, how do we get that? How do we get slopes of an F-graph? Well, that's where this is going to come in. Now, over the course of the next week, we'll be just estimating. We'll draw ourselves little triangles and do rise over run. I mean, sometimes that's the best we can do. Okay? When you draw a tangent line, think of it, I think your book talks about, think of it like headlights on a car. Think of a car driving along a curvy road. And the tangent line's like where the headlights and the taillights would point, out that way. So the tangent line, it just kind of follows the graph. All right? Now, this would be a good time probably to send you this document. So if you're all logged in, hopefully, looks like one person's not logged in. Somebody not logged in? See if you get this. Everybody should get this document. I guess I can see who's logged in. Go ahead and open it. Courtney, you logged in? Maybe we should have taken bets earlier. First. Who's not? Just try. Just try it again. All right, yeah, when it comes up, just hit open, and it should open right up. There she goes. Now well, you buy it. Sometimes it does. It just kicks you. Now, why it always does it just to you, I don't know. All right, so let's go ahead a few pages. So if we hit Control right arrow. Now, what we have, if you hit Control right arrow to the second page, what you have is an F graph here. The red one above is the F graph. The blue one is the F prime graph. Okay, let's keep going. We'll right arrow again, control right arrow till we get to page 1.4. Okay, so now you should have this, right? Now, really, there's nothing, no assignment with this or nothing you have to do. I just give this to you so if you want to get on this and kind of mess around with it and see what it's saying, but it sort of allows you to actually grab on and do something with it. But if we go, you can do two things. You can grab this little white X dot right here, but probably easier is to go over here to this little up and down arrow and just hit the little up arrow. Now, what I want you to notice is this blue line here has a slope. It's positive. It's fairly steep. It's 3 point something. Down here, notice what we have is we have a dot where we've plotted 3.12 as our y value. Now, when we hit that little up arrow, it will make our line go to the right a little bit. And what's happening to that blue slope? It's getting less. It's still positive. This graph is still going up, the red graph, F graph, but the slope is getting smaller. And look what's happening on the blue graph. It's going down. It's still positive. But again, I'll say it one more time. The slopes of this red graph are being plotted down here on the blue graph, and that is our derivative graph. So we keep going, and we get to 0, and sure enough, right here at the peak, the slope is 0, so the derivative graph crosses the x-axis. You can see why we'll be interested in roots, because it looks like the roots of our derivative graph correspond to our local maxes and mins on this graph, and that is going to be something we will use that connection a lot. Now our slope on the red graph is getting negative, and so we see on the blue graph that dot is going negative and more negative. Now what happens right here? That is an inflection point, which means our slope was getting negative, more negative, more negative, more negative, more negative, steeper, but now what? Now it's negative but getting less negative. And we're going to talk about what that means. What do you mean less negative? Well, to me, less negative is like -4, -3, -2, -1. To me, that's less negative. It's going towards 0. So our slope, our blue line is going towards more horizontal, and so our blue graph is coming up towards 0, the y value. And right there we have a slope of 0. And then so forth. Okay, so just understanding this connection here with slope. Now, let's go back to this picture from our book. All right? Now, we looked at this as far as miles per hour and speed. Now let's look at it in terms of slope. Well, I guess we did that a little bit, didn't we? So this graph is positive slope on the two blue areas. The slopes here are positive above the x-axis. Here the graph's going down, so it has a negative slope. Here the graph is negative. Now we're not going to worry right now about where this graph's going up and down and what that means. Okay? But for right now, we'll just stick with those kind of simple connections. All right. So derivative has basically two definitions, rate of change of f or the slopes of f. Which one you think of depends on the problem. If you're thinking of the story problem with units, you think of rate of change. If you're thinking of it just as a graph that has no context to it, you would think in terms of slope. Okay, if you turn to page 41, I got two other things to talk to you about, and then hopefully 15 minutes or so, and then we can get into some work time. All right. So the first, seems like I'm missing something here, because it seems like we're ahead of schedule a little bit, but that's okay. I think we're good. All right, so here's the first one. This is on page, this is at the top, kind of towards the bottom, I guess, of page 41. Bottom of page 41. There is an equation or two here that you need to be familiar with. Now, this part doesn't take much, if any, calculus. Doesn't have much to do with calculus at all. This is, but these are kind of special equations that deal with an object in free fall. So if I throw a ball up in the air, okay, the only thing acting on it is gravity. This is what we mean by free fall. Or if I just drop something, okay, free fall. So there are some equations that go with this. The height of the object is given by this equation right here. Now there's two of them there. One of them is if you're using meters, and one of them is if you're using feet. I think the problems in our homework deal with feet. Okay? And the 16 comes from the acceleration of gravity. Acceleration of gravity is 32 feet per second squared. So this part of the equation is half gravity. So on the other one, it's 4.9, which is half of 9.8. 9.8 is the acceleration of gravity in meters per second squared. Okay? But anyway, that's where that comes from. So if you're using feet, this would be your equation. Now, h sub 0 is your initial height. So this is the height that you throw the object from. And v sub 0 is your initial velocity. So if you just drop the ball, the initial velocity is 0. You throw it up or you throw it down, it would have an initial velocity. Throw it up, it'd be a positive initial velocity. Throw it down, it'd be a negative initial velocity. Okay, so that's what those two parameters are there. So this would be the height function of that object. So they're going to give you a situation. They're going to tell you the initial height. They're going to tell you the initial velocity. You plug those in. Maybe use your calculator to graph it if you want to. And you're going to answer some questions about that situation. Okay? Now, the velocity of that ball also has an equation. But now, how that connects with what we're doing is another name for the velocity would be h prime. For some reason, my pen there. H prime. So the velocity equation, another name for that will be h prime. It's the rate of change of the height. And that is v sub 0 minus 32t. And again, v sub 0 is the initial velocity. Okay? All right. So you're just going to have to use and work with those equations in some homework problems. They'll give you information to plug into it. You'll have to either solve an equation, which you can use your calculator for if you want to go do a solve on the calculator screen, or if you want to graph and trace and whatever, you should be able to do it. So several of the problems in the homework deal with these equations. All right? So I just want to point those out, and then you should be able to work with them from there. All right, the next thing I want to talk about, and this is the more complicated one, especially in the beginning. The terminology is extremely complex, but we're going to try to break it down. And it's going to seem, I'll be quite honest, when we get done with it, it's going to be like but as we go along, it'll pop up, and hopefully, as we go through the year, you'll be like, oh yeah, that's speed limit. Yeah, that's speed limit. I recognize that. That's speed limit. Okay? Hopefully that's what happens. So when we look, this is over on page 42. This is over on page 42. All right, now I'm going to reword it a little bit from what's on page 42. So here's how this is going to look. So if f prime of x is less than or equal to capital M, comma, for all x in the closed interval AB. Okay, let's write that. So far. If f prime of x is less than or equal to m for all x in the closed interval AB, then f of b minus f of a is less than or equal to m times the quantity b minus a. Smiley face, and it is not factor. Exclamation point, smiley face, and what else? I don't know. Or is that a wink? Can I do a wink? Heart. All right. So, right, it's a whole lot of mess, right? Somebody one year said, how could that even be math? There's not a single number in anyway. Not that whole thing, there's not a single number. Okay? Okay, so what does this mean? Well, let's try to interpret this. Well, what we're going to do is we're actually going to interpret it two ways. We're going to interpret it one way using rate of change, speed, and we're going to interpret it another way as slopes and see what this is saying. Now, again, I'm going to be honest with you up front. What it seems to say seems somewhat obvious, but it has ramifications. Sometimes some of the most important things in math or some of the most important discoveries of science, after they're discovered, seem somewhat obvious. But that's after they were discovered, right? So let's go through it. So in the blue, I'm going to first do rate of change. So what does f prime mean? Let's do a position velocity situation. Miles and miles per hour. Okay, so what does f prime mean in that context? Miles per hour, speed. We'll call it speed. Now, technically it's velocity. Okay, technically it's velocity, but speed will be okay. Speed will be okay. Okay, so this is going to be speed. And then this is just some number, m. So if we say the speed is less than or equal to 20, if I tell you that I'm driving in my car and the speed is always less than or equal to 20, what would you call 20? The max speed, right? That'd be your speed limit, right? That's what's called the speed limit law. What's that?
Speed suggestion.
Yeah. Oh, well, yeah. I've seen some of you guys drive. You're right. Okay, but this is not a suggestion, right? This is actually not. This is true. All right. How fast you drive your car? That's a whole nother story. So this would be. Let's call this our max speed. Speed limit, right? This is the most we could go. Right? The most we can go. The fastest we can go. All right. That's what m is going to be. Right? So our speed has got to be less than or equal to our max speed. Now, all this over here just means for all x in AB, x is like time period, and A is the beginning and the end. So this just means for all of the time from the beginning to the end, we're going to stay below 20 miles per hour. So that's what that means. Okay, now let's look at this. Now let's draw ourselves a graph. This might help us. So I'm going to draw off in the corner here. I'm going to draw a little graph here. And this is A. This is the beginning of our time period. And then here's B, which is the end of our time period. Okay? And so here's my graph, whatever, I don't know, it doesn't matter what the graph does really. We'll make it simple, we'll just make it a graph that just kind of goes up. Okay, so right over here would be f of A, right? And right over here would be f of B. Now remember, we said this is going to be miles, right? F was going to be miles, and f prime was our speed. All right. So what is f of B then? What does f of B represent in this situation?
The last speed.
Not quite distance I traveled. That's the closest thing I heard. It's the position when. At B, when's B? At the end, right? A is the beginning of our time period and B is the end. So f of B is my position at the end. What's f of A? My position at the beginning. What's f of B minus f of A? The difference between where I stay. Now let's keep it simple. We're going to go in one direction. It is displacement technically, but we're going to just say we're going in one direction. We're not turning around. So we'll keep it simple. So f of B minus f of A, my ending point minus my beginning point, wouldn't that be how far I went? Okay. So f of B minus f of A would be how far I went. Okay, now you're right. It's technically displacement. It's technically it's a distance from where I started to where I ended. If I change directions, that wouldn't be how far I went. Okay, but we'll just keep it simple for right now. Turns out it works no matter what. This law is going to work no matter what. It just gets more complex to put into common language by doing it. All right. And what did we say M was? Max speed. Okay, and then what's B minus A? The time it took. How long I went. So how far I went, how long I went. How long I was driving or whatever. Now, let's put this together with some actual numbers here. So let's say 20 was my max speed, 20 miles per hour. And let's say I went for 3 hours. So B minus A is 3. Max speed is 20. Times those, you get 60. How far I went has to be less than or equal to 60. If I tell you that the most I went was 20 miles an hour, and I did that for 3 hours, the farthest I went was 60. Seems fairly obvious. But that's what that says in plain language. The importance of it is this. The importance is this. If I tell you something about the speed, you can then know something about how far I went. That's what the speed limit law is saying. So if you want to encapsulate this, put it in your notes, I don't care. If you want to encapsulate the speed limit law, that's what it would say. If you know something about how fast you're going, you will know something about how far you went. Makes sense. But in the black, all that math lingo, that's what that's saying. It's kind of important to be able to read that math lingo. You think about how we interpreted that and how we thought through what each thing is, those things meant. It started to make sense. Now let's talk about in terms of slope. Let's talk about in terms of slope. The other important thing this has done is connected f prime with f for us. If we know something, basically it's saying if we know something about f prime, we can tell something about f. If we know something about f prime, we can find out something about f. Okay, let's talk about in terms of slope. We'll make this red. So now instead of f prime being speed, f prime is, no, that was speed. Slope, right? So now, again, go back to this. F prime is either rate of change, like velocity, or it's slope, right? Those two are interchangeable. So now we're going to talk about f prime being slope. So what is m? Not our max speed, but our max slope. Now what does slope measure? The steepness of a graph, right? So let's, instead of max slope, let's call that max steepness. So m now is our max steepness. All right? Now let's go down here. F of B minus F of A. Now let me draw this a little differently in red here. See if this gives you a hint. It didn't help the other class very much, but I think they're just kind of quiet. What's another name for F of B minus F of A? Wouldn't that be this right here? In slope language, what is that right there? Rise. That is the rise. So another way of thinking of F of B minus F of A would be the rise of F. The rise of the F graph. Or how far up the F graph goes. Of course, slope's negative. It could be how far down. All right? So F of B minus F of A is the rise of F. M was our max steepness. Right? And what was B minus A in slope language? Look at my picture. B minus A would be the run. Oh, okay. If we take the steepness, of course, we know slope is rise over run, right? So M is slope, so it's rise over run. If you take rise over run times run, rise over run times run, you get rise, right? So what this is saying is that if you have a graph where you know the steepest it ever is 3. The steepest the graph ever is 3. And you, remember we said, and we went for 3 hours? So let's say the steepest the graph ever is 3. And we go over on that graph 5. What do you know? The most it could have went up is 15. If the steepest the graph ever is 3, and that's what F prime tells us, and I go over 5, the most I could go up is 15. But it might not be 3 the whole time, just like I might not have went 20 miles an hour the whole time, right? But that's what it says. So this says in slope language, it says if you know something about the slope of F, then you know something about how fast F is going up or down. How far F is going up or down over a certain run. Okay? All right, so the blue is rate of change language. The red is slope language. This is called the speed limit law. There's going to be some problems. Now, those are going to be the ones you'll probably struggle with the most just because of the language and reading the notation. Okay? But do the best you can with that, and we'll get better at that over time. We'll definitely be talking about those tomorrow. Okay? But do the best you can. All right, you got the rest of the time? Oh, yeah. That is good. Yeah, I don't mind it. You guys have done a good job of working. All right, 1.4 homework questions. Now, they're going to start out they should be pretty simple. The tendency is to overthink them. It's going to start out with just some notation questions. It's going to ask you about the Bismarck graphs a little bit, I think, too. And it's going to have you interpret that lingo. And don't make it harder than it is. Okay? When I was talking about the V graph was what? Was P prime. They're the same. V and P prime are the same thing. Okay? So, go ahead and work on that. And we're done with the hats, I guess, so you can probably take those off.